I will put 0 inside my equation here. So exponent negative 0. Exponent negative 0, because my initial value is 0. So the answer is equal to 1. Okay, so I get the answer of 1, but actually it's my true value supposed to be 0.56. I get 1, so this means the error is going to be really huge. True value minus the result over the true value, so the answer will be a lot of error in there. So now I will go for the next iterations. To go for the next iteration, x no more is equal to 0, x is equal to 1, because you already found it here. So you're going to use this value as a next input for the second iteration. For the second iteration, xi plus 1 will be equal to a exponent negative 1. So I take this value, I put it here. So the answer will be equal to 0.36. So when you are going to compare with the true value, still the error is going to be huge. So you will go for the third iteration. But for the third iteration, you are going to use this value as an input. So for the third iteration, xi plus 1 will be equal to exponent negative 0.367. So these values is getting in here. So I get the answer of 0.692. I think now you can imagine if we are going to go for the, if we are going to go through the, what I call it, the fourth iterations, which value are going to use? We are going to use this value inside the equations to get a new answer. So you are going to do so till you are going to make some values of tolerance error, or you are going to find no changes, or you are going to find the values. Like for my case in here, this is the approximate error, and this is the relative error. Relative error because I have the true value. Approximate error, that's mean new result minus the old one over the new results. So you can see the iterations from here till down there. You can see it's at the, after 10 iterations or 9 iterations, I am almost getting the answer of 0.5649. So this answer here, it's closer to the true value. That's why it's the error, it's less than 0.5. Okay, so this is the fixed point iteration. Okay, I'll give you about a time to try to solve the, try to find the fourth iteration. What's the answer is going to be? You're supposed to get the answer of 0.5005. This is supposed to be your answer. If you have any questions, please ask. Any question? Can you get the values? Okay, so the conversions of the open methods could be happen in a form of staircase or oscillating mode. Same also the divergence could be happen in a form of staircase or oscillating mode. So if you are looking at the conversion in a form of staircase, this is your initial value. Your next point that you're going to find is x1 and x2. So you can find that these things is happen in a form of staircase towards finding the roots of the equations. Same also goes with the conversion as oscillating mode. This is x0, this is x1, this is x2, this is x3. So you can see that it's moving around to achieve the point. This is considered conversions. Diversion, this means you're not going to find the root of the equation. So you can see that it's happening. This is x0, this is x1, this is x2, and you can see that it's getting away from the root. So that means you're not going to find this point. Could be also happen in a form of oscillating mode. So how actually you are going to overcome if you are going to find that when you are solving, let's say for this example, if you are solving this one, but you are not finding this value anymore, and you can see from there it's diverged, that means the error, instead of the error, it's reduced. You're going to find the values is increasing. So that means it's diverged. So how you are going to overcome this problem? To overcome the problem of the divergence, so whether you're going to choose a different initial value, or you are going to modify the function into another form, or you are going to choose another method. Actually, you cannot do number one, and you cannot do number three. Because when the question is coming, you have to follow the exact initial value that we give in the question, and you have to follow the exact method that we are putting in the questions. The only way to do that is number two. Modify the function into another form. What does it mean? Let's back to the first slide here when we are talking about this equation here. Okay, remember when we are saying that it's simple fixed point iteration, what you need to do is you need to move an x and put it on the left side of the equation. So in this case here, we choose this value of x, so we are getting this equation in here. So we are trying to solve. While you are solving, if you see the error, it's increased and you are diverged from the root, so you need to stop, and instead of selecting this x to be rearranged, maybe you are going to select the value of x squared. So that means this is the meaning of, so here you are going to find the root, something like that. Okay, so this is the meaning here now of modify the function into another form. Okay, so the next method for today, it's the Newton-Raphson method. This is the most widely used methods. It's more efficient than the fixed point, and it's more faster. It's based on the Taylor series expansion. If you all remember, is the Taylor series expansion that you're saying it's the more term that you are adding to the calculation, the more you are going to get an accurate result. Okay, so this is the Taylor series, if you remember that. In our case in here, we are going to, by the way, you are not going to be asked to derive the equations in the exam. Okay, so I will just only explain it, but you are not going to be asked to derive the equations. Okay, so if we are taking the Taylor series from this term to here, so this one will include the first derivative of the function and the step size delta x. So if we are going to get the delta x, that means the initial value minus or xi plus 1. So this is the delta x here. If we are going now to rearrange, remember that it's for simple fixed point, or what we need to find, we need to find x plus 1. So if I'm going to rearrange this equation here based on this x plus 1 to put it here on the outside, so what I'm going to get, xi plus 1 will be equal to the initial value of x minus the function over the first derivative of the function. Okay, so this is Newton-Raphson equation. So don't memorize it. It's going to be given in the midterm and also in the final exam. But how these things came, I explained it, but you're not going to be asked questions how to derive the equation itself. So this is the equation of the Newton-Raphson method. Okay. So this is our first example here using the Newton-Raphson methods to be solved. We are going to follow the same example from the previous. This is the function. It's equal to exponent negative x minus x. And we are also here, we are going to start with the initial value of x is equal to 0. Here, the question or the example asking us to iterate until the percentage relative error it's less than 0.05. Not 0.5, 0.05. We are making it here like this because it's Newton-Raphson, it's more accurate than the fixed point. So, and the true value it's already giving to us. So remember, the equation for the Newton-Raphson, you need to have the first derivative of the function. So that means I need to find the first derivative of this function here. So the first derivative of this function will be equal to negative exponent negative x minus 1. So now if I put the function, if I put this function, and I put the first derivative of the function into the Newton-Raphson, so what I'm going to get, x plus 1 will be equal to the initial value of x minus the function over the first derivative of the function. This is the function, and this is the first derivative. Then I will start to solve based on the initial value. Let's see it how step by step. So this is a function, and this is the first derivative. So Newton-Raphson, that means I need to have the function and the first derivative. So it's going to be the function, and this is the first derivative. Okay, first iteration, our initial value of x is given in the question is x is equal to 0. This is the initial value. So when x is equal to 0, I will put zeros in all the x's here. So I'll put 0 here, 0 here, 0 here, and 0 here. So 0, negative 0, and 0, and negative 0. So the answer is 0.5. When you are looking at the first answer is coming from the Newton-Raphson, from the first iteration, it's 0.5. Our true value is equal to 0.567. So this means it's more closer. So this means from the first iteration, our answer is more closer to the true value. Okay, so now we will go for the next iteration. For the next iteration, x no more it's equal to 0, x is equal to 0.5. So I'm going to use this value of 0.5 into the second iteration. So xi plus 1 will be equal to 0.5 minus exponent negative 0.5 minus 0.5 over negative exponent negative 0.5 minus 1. So the answer is 0.5663. Okay, now it's more closer to the true value. If you go for the third iteration, by using this value, you put it here, and here, and here, and here. So you get the answer is 0.5671. When you are looking at this value is exactly the true value. So the error will be equal to a 0. You can see it from here. It's at the third iteration. You already achieved the answer, and the error is 0.0002. Okay, so it's more faster. We have solved this example using the fixed point. It's about 9 or 10 iterations to be more closer to the true value. But with the Newton-Raphson, we just only go for the 3 iterations, and we already achieve the answer. Okay, let me give you a time. So try the example to solve. If you have any questions, please ask. Is this example also in the textbook? I will give you the time. If you have any questions, ask.
No, doctor.
Okay. Okay, the last method for today, which is the second method. It's a slight variations of Newton methods, and somehow it's more efficient. It's like efficiency of the Newton-Raphson, but it's a little bit different because here for the second methods, we are not going to use a derivatives as Newton-Raphson. So it's a slight variations of Newton methods function whose derivative are difficult to evaluate. So for this case, instead of we are going to use the derivative as Newton-Raphson, we are going to use the backward finite divide difference value. If some of you still remember what is this value, remember last time you were talking about if you are having an initial value of xi, most of the time you are trying to find xi plus 1, which is this one, we call it is the forward finite divide. But in the case of the second methods, it used the backward finite divide difference instead of using a derivative. So this means second methods, it used the backward finite divide. This means it's using xi minus 1 to help us to find a new value of xi. That's the meaning of second methods. It's using the backward finite divide difference instead of using the derivative same like Newton-Raphson. Okay, this one will be clear when we are going to use the example. But there is something here before we go, is how actually you're going to find xi plus 1 using the second methods. It came based on this equation here. And when you are going to look at this equation here, it looks familiar because this equation in here, it's going to draw for you a linear interpolations between x and its function and x minus 1 and its function. So it's drawing for you this line. So if you remember this equation in here, it's exactly equal to the same equation for the false position method. It's exactly the same values, but here second method and this is false position methods. Okay. So second method, it requires two initial value, x and x minus 1. Remember that we are saying here we are using the backward finite divide difference. So this means when the question is coming for the second method, you are going to have two initial value of x and x minus 1. So you are going to find the value of x and also x minus 1 to find the new value of xi plus 1. This is our target. So we need to find this value. So it requires two initial values. But maybe some of you are going to ask me, Sarah, you are saying from the beginning it's open method, it's supposed to be starting with single initial value. Yes, but second method, you need to use two initial values. Maybe someone is asking me, then if two initial values why we are not classified as a bracketing methods. Look at here. I'm going to, let me just delete all these lines. Why we are not classified the second method as a bracketing method, since we are going to have two initial values. The answer is, remember that it's for bracketing methods. You suppose you are going to have a value of x lower at this position and x upper at this position. And between x lower and x upper, the root will be lie between these two values. Must. Okay. But in my case in here, if you are looking at the second method, what do I have here? I have the value of xi initial and xi minus 1 backward at these two positions in here. But between them, there is no root. The root is totally different from, it's not between them. If the root is between them at this position, so that means this is considered as a bracketing methods. But since the root is not between them, so that means that's why it's classified as an open method. So the second method has the same properties of Newton method. Conversion is not guaranteed for all the x's. So let's try to solve the same example that we solved for the fixed point Newton-Raphson, and solve it again using the second method, and to see how efficient also to solve using the second methods. Within 2 or 3 iterations, we are going to achieve a value that it's near to the true value here. Okay, what we are going to see the difference here is that we are going to have two initial value, xi minus 1 backward and xi initial. So we are going to have two initial values, 0 and 1. So the example asking to iterate until the true percentage relative error it's less than 0.05. So how we are going to solve? Let's see how. Okay, so this is the function. This is our initial value, x minus 1, and initial value of x. And this is the equation of second method. So we need to find all these parameters in here to put inside the equation to find the new value of x plus 1. Okay, so first iteration. X initial is equal to 1 and x backward is equal to 0. So I need to find the function of x minus 1 and the function of x. Function of x minus 1, this means the function when x is equal to 0. So I put 0 here and 0 here. So exponent negative 0 minus 0, so the answer is equal to 1. Now I need to find the function of x. So x here is equal to 1. So that means I need to find the function when x is equal to 1. So exponent negative 1 minus 1. So the answer is negative 0.63212. Okay, so now I have all the values that I need to put inside this equation here. I have the value of x, which is 1. I have the function of xi, which is negative 0.63. I have xi minus 1 minus x, so that's mean a value of 0 minus 1. I have the function of x minus 1, which is equal to 1. And I have the function of x, which is negative 0.6. So I'll put all these values to find a new value of x plus 1. Okay, I get the answer. The answer is equal to 0.6127. This value, it's not closer to the true value. So when you calculate the error, true value minus the result over the true value, so the relative error is 8%. That means I need to iterate one more time because the tolerance value it's given in the question, it's less than 0.05. So I will go for the second iteration and I will move the data like this. So in this coming iteration, xi minus 1 will be equal to 1. So that means this value will replace this value. And x will be equal to 0.6. So that means this value will replace this value. Then I'm going to find the function when x is equal to 1 So it's negative 0.6321. And I need to find the function when x is equal to 0.6127. So exponent negative 0.6127 minus 0.627. So I get the answer is negative 0.0708. So I will put those four values inside the equation of Newton-Raphson, second method, to find a value of x plus 1. I put all the values. I got the answer 0.5638. When you are looking at this value, it's closer to the true value. So when you calculate the error, true value minus this result over the true value, it's 0.58. But still, remember, it's the example asking us to iterate till the error it's less than 0.05. So I will iterate one more time. So this value will be gone, will be replaced by this value, and this value will replace this value. So here it's 0.6127. X is equal to this value here. So I need to find the function of this value. So the answer is negative 0.0708. And I need to find the function of this value. It's 0.0518. So now I have the four values I will put inside this equation to find a new value of xi. So the answer here, 0.5671. Look at this value and compare it with the true value. It's almost identical. That's why when you're going to calculate the error, it's 0.0048%. Okay, so within 3 iterations, also we found the answer same like Newton-Raphson method. Okay, so now before we finish this class in here, there is a comparison between first position method and second methods. Why actually we are making the comparison? Because both of them, they are using the same equations to find a new value of x. But so what's the similarity here? The similarity between the two methods, both of them, they are using two initial values to compute approximate one. Okay, the difference is how one of the initial values is replaced by the new estimate. For the first position methods, we are looking at if the function of x lower times the function of xr is greater or less than 0, we exchange the values. But for the second methods, as we saw from the example in here, the data is going to be replaced. X will replace x minus 1, and x plus 1 will replace the value of x for the coming iteration. So we are like shifting the data to be up. Okay. Graphically, when we are going to compare the two methods together, at the first initial values or the first iteration, both of the two methods, they are identical, exactly the same. But for the next iterations, you're going to find that it's first position methods, it must find the root, but for the second method, it could be diverge from the root. So this is the difference in here. First iterations, both of them technically identical, but the second iterations, it could be for the second methods, it's diverged from the roots. But for the first position, it will find the roots and anyhow. Okay, this is an exercise. You suppose you are going to do it if we are having this one in the class or in the lab tutorial. So I was going to be with you to solve it and show you the answer. But since we are online, try to solve. And if you have any questions, please ask about it. It's not for long. This exercise asking you to determine the highest real root for this function using the fixed point iteration, and also using the Newton-Raphson, and also using the second methods. Here, there is no value of the tolerance error. You need to just only iterate for 3 iterations only. So 3 iterations for fixed point, 3 iterations for the Newton-Raphson, and 3 iterations of second method. Okay, so try to solve. If you have any questions, you can discuss with me. Or you can WhatsApp me anytime. Okay, Before I leave, I just want to ask, do you have any questions about those methods?
No, sir.
Okay. Another thing I want to tell you that if you open the ufuture.item.edu.my at the course forum, yesterday I uploaded a video is talking about the same examples that I have done here, like open methods. So again, to see the fixed point iteration and also example Newton-Raphson second methods and also example of how to solve. It's the same example I showed here. Just click on the link. You are going to see the
Hi everyone.
the videos.
In the bracket, which is a simple fixed point item. So in this case, you can read in order for you to use simple fixed point. So this is one equation, and then the approximate error. Then you need to check important.
So this is the
need
method.
to check whether your G prime X.
And this is, I think, the example that I just explained right now.
Okay, so now I would like
This
to
is the
show one
exercise.
example. Have a single
So
two.
try the exercise by
Know whether
yourself
this is
before.
the value 3. This is the
And you can check your answer
GX
with the
formula.
video here. So I think that is most of you can access the ufuture platform. Okay, so that's all for our class today.